Hello, today we're going to get started on some of the basic course material. Some of these are fundamental ideas that we will revisit over and over again, so we really want to get a good foundation. We normally start any science class off with the idea of the scientific method. Now, I'm not going to spend a great deal of time on the scientific method, not that it's not extremely important, but the book does a great job of explaining it, and it's a fairly straightforward idea. But I do want to kind of hit the highlights very quickly and clarify one or two quick things. So here's a rush version of scientific method. We could literally spend an entire semester on this topic because of its complexity, but we'll start here. The simplest definition I can give you for scientific method is it's a way of thinking. It's not the only way of thinking, it may or may not be the best way of thinking, but it's a way of thinking. It's very systematic, it's very logical, and it's what we use throughout the sciences. So here's kind of the short simplistic version of it. The first thing you do in the scientific method is you take observations. We look at the world around us to see what goes on, and we do this with a great deal of data. And when we think we've seen enough, we come along and we make hypotheses. And one of the best simplistic definitions for a hypothesis, is an educated guess. But a hypothesis takes this idea that under these conditions, this is what I predict will happen, or this is my expectation. That's purely kind of an analytical idea. It's something you think of. It's not necessarily always right by any means. And so from there, from the hypothesis, we go to the experiment. And this is where things get tricky and sometimes confuse people. If we were sitting in the regular classroom, I would ask you, what is the purpose of a scientific experiment? And usually someone will fall for the trap and say it's to prove you're right. And we make a big deal about it because this is the key point. Science never ever knows it's completely right. Science has probabilities and they think it may be right, but we never know anything with certainty. You cannot prove something right in the sciences, and that's a very important distinction. When you do an experiment, there are two possible outcomes. If any of you have actually taken statistics in the math department, you'll do something called hypothesis testing, and in that the two outcomes are you can prove your hypothesis wrong, or you can fail to prove your hypothesis wrong. You never prove it right. So when we do an experiment in the sciences, we normally do the experiment multiple times, and so after the experiment we go back and we reassess our hypothesis. If the experiment proved us wrong, we modify the hypothesis to account for the new observation. If it doesn't prove us wrong, we repeat the experiment with different conditions and different circumstances as many times as we can to look at the pattern. If a hypothesis holds up to testing for a long period of time, it will eventually become more trusted and more commonplace within the scientific structure. You'll sometimes hear people use the term scientific fact. I will use it on occasion. It's actually a very incomplete term. In science, there are no absolute facts. It's just things that have withstood a great deal of testing. For example, gravity is something that we all have a huge amount of experience of. If you let something go, it will fall to the ground or fall downward. Obviously, this has been demonstrated billions and billions of times, so it led to kind of a common expression that was something to the effect of what goes up must come down. And of course the assumption in that is it doesn't hit anything. But the idea was if something goes up, it must come down. And this was believed with very high probability for a very long time until we sent our first early rockets into space. And then we realized if something went up with less than escape velocity, it would come down. But if it went up with greater than escape velocity, it would not. And as we go over time, scientific ideas develop and change and enhance based on new information. If you've taken physics, you may have studied Newtonian physics based on the work of Sir Isaac Newton. Newtonian physics is still taught very heavily. It's kind of the centerpiece of Physics 1 usually, and most of it is incorrect. We've shown that it actually doesn't hold up to scrutiny for certain types of objects that travel at certain speeds, but it's a very good model. Because that system has kind of changed over time, we've developed other versions, including quantum mechanics and statistical probability and string theory, which explain observations in a much more complex but fitting way. The problem is those calculations and those models take huge amounts of computer space, and Newtonian physics works fairly well for normal size objects at normal speed. So we still teach it. So I kind of want to leave this here, and I do encourage you to look up the difference between a scientific law and a scientific theory. Very important. But I just want to highlight, in the scientific method, we never know that we're completely right on anything. Science is inherently skeptical. So with that quick kind of overview of the scientific method, we noticed that the very first step were observations. And a lot of the times the observations will involve actually taking measurements. Now, of course, you can have qualitative observations that do not have numeric values, or you can have quantitative. But we'll focus fairly heavily on the number-centered ones. And so what this is going to lead us to next are our scientific units. There are several unit systems out there. We're going to discuss two of them to some degree, and one we might mention. The first of these, and I'm going to switch over to pen here. The first of these is called the SI system. Now the SI system, the international system, is the metric system that you're probably somewhat familiar with. There are actually more than one version of the metric system. I'm going to skip over, so leave some space if you're writing this. Third system is sometimes called the English or the imperial system. These all have multiple names. And just to kind of confuse a little bit more, this is sometimes called the FPS system. This is called the MKS system. You'll see why. And another system I'm just going to mention very briefly, just so I want you to know it exists, is called the CGS system. It's another of the metric variants, and it's used in certain fields. We're going to spend about 90% of the class on SI units on the left side, maybe 10% mostly in this first chapter on English and Imperial, and CGS we really won't approach. I just want you to know it exists. So what has happened is scientific groups have come together and they've come up with quantities that can be measured, that from which you can get everything else. So over here we're going to have quantities. There are 7 basic quantities in these systems. We're going to focus on some of them for right now. The first basic quantity is length, mass, and time. We'll mention the others later, but we're going to spend a lot of time on length, mass, and time. And so in each of the unit systems, there is a basic or fundamental unit. So in the SI system, the fundamental unit of length is the meter. I changed my pen width there. So the meter is abbreviated with a lowercase m. It's very important to note that we will use letters more than one location, and uppercase and lowercase are different. Sometimes, for example, I have lines on this paper, so it's fairly easy to tell, but sometimes we'll put a bar over a symbol to show it's lowercase just for clarity. We'll use the bar for other things as well. But the fundamental unit of length in the SI system is a meter. In the CGS system, it's a centimeter. And in the English or imperial system, it's the foot. And you'll notice those are the first letters of the 3-digit or 3-letter codes also. As we go through this course, there are certain analogies that I'm going to use at different times just to make a point. And one of those things that I do is called the 5-year-old or 5th grader questions. These are the things that your nieces and nephews, cousins, children, they're questions they ask you that you think you should know the answer to, but putting the answer into words is difficult because it seems so obvious, or you didn't have a great view of the bigger picture. It kind of catches you off guard. Here's kind of a simple example. If I ask you to define the word length without using the word length or long. Sometimes it takes people a few minutes. Usually they'll start talking about the distance, which is a way to do it, distance between 2 points. What if I move down to mass and ask you to define mass? Now in physics, they'll start out with a simplistic definition of mass, and eventually they end up at a mathematical one. But the simplest definition of mass, which is pretty accurate actually, is how much stuff you have. It's not how much space it takes up, it's how much material there is. So the material could be packed in a tight space or let loose, but it's how much stuff. Fundamental unit of mass in the SI system is the kilogram. The fundamental system in CGS is gram. And in the English system, instincts would tell you it's something else, but it may be something you haven't seen before. The fundamental unit of mass in the English or imperial system is the slug. And it's not likely that you've heard that one before. We're not going to use it heavily, but we do need to know it exists. All three of these systems use seconds as their fundamental unit of time. Now, like I said, there are 7 basic quantities in each system, and we'll see them in a moment. But what we're able to do now is combine those fundamental units, usually by multiplication and division, to make new units. So these are derived units, or derived quantities, I should say. And we'll still have the fundamental units in those. So for example, if I want to measure the area of something, if it were a flat whiteboard or something like this screen, most people would tell me to get the area by doing length times width. Both of those are just actually lengths, just different words for them. So area is a length squared. So in the SI system, the fundamental unit of area is a square meter. CGS, it's the square centimeter. In English, it's the square foot. Volume is similar. Volume is a cubic term. So if you have cubic lengths, it's a volume. And the common volumes, the base units, are cubic meters, cubic centimeters, and cubic feet. I want to clarify there are lots of other units of volume we're going to use. They're just not the base units. So perfectly valid to have other units, they're just not the base units. We could extend this for some time. If I say this in front of a physics professor, they will have a heart attack. So if you're a physics professor, don't listen to this next part. But for this class, we're generally going to treat the two ideas of velocity and speed as the same. They're not the same, but for our purposes, they're close enough for what we're doing. And you pretty much know that speed is this idea of distance over time. Velocity is displacement over time. So the fundamental unit of speed in the SI system is meters per second. We just took the fundamental unit of length and divided by time. Centimeters per second, feet per second. And again, miles per hour, kilometers per hour, those are other units we'll use, they're just not the fundamental. Acceleration. Acceleration is the rate at which a speed or velocity changes. And acceleration is just the speed divided by time. So it is meters per second squared, centimeters per second squared, and so forth. And you get the idea of how we can put these together. I do want to show you a few more that are going to be important to us as we go, and we want to kind of introduce them early. One of the ones we're going to use fairly often is force. Force, if you have to kind of define it, is a little difficult because most books do it as a push or pull. That's bugging me. Let me correct that. But force, and you may have seen this equation before, can be treated as mass times acceleration. So in the SI system, mass is measured in kilograms. Acceleration is in meters per second squared. So in the SI system, force is measured in kilogram meters per second squared. That's kind of a mouthful, so we give that a name. That is a Newton. A Newton is just the term for kilogram meters per second squared. In the CGS system, it is gram centimeters per second. That's called a dyne. Not something we'll use again, just so you know. I'm not going to ask you about anything in CGS. And in the English system, mass is slugs. Acceleration is feet per second squared. So slug feet per second squared is the imperial unit of force, and this has the shorthand name of pound. It's abbreviated LB because the Latin Libre. So that's where the P and FPS comes from. Now we could continue deriving other derived units such as working energy or pressure, and we will do that as we go on to the course, but let me just kind of show you a graphic. This is from the National Institute of Standards, and this shows the relationship between the SI units and how they're set up. So I told you that there were 7 basic quantities. The 7 basic quantities on the left side here are length, mass, time, which we've talked about, amount of a substance, which will be measured in moles, that'll be an important one for us, electric current, thermodynamic temperature, which is in Kelvin, and luminous intensity, which refers to light. So we'll focus on the top ones now. But in this chart, the 7 fundamental or base units are on the left, the derived units are on the right. The solid lines indicate multiplication, the broken lines indicate division. So for example, volume is just length times length times length, cubic meters. Area is square meters, and we looked at these. Force was a kilogram times a meter per second squared, so it was mass times acceleration, and it has its own name of Newton. And you can see we will work with joules and pascals and watts as we go along. We will mention coulombs briefly, and of course we'll talk about temperature, but a lot of these others we'll talk about in later chemistry classes or physics. This is just a representative chart. You don't need to memorize every one of these, but I do want you to have kind of a place you can see this. This is in the course shell if you want to look at it, but you do not need to memorize it, of course. The last thing I want to say about units is that they're critically important in the problems we do. You need to show your units at every step and keep track of them, because a lot of the time they will be very significant to the outcome. So don't minimize units or just try to put them at the end. We want to keep track along the way. I'm going to stop this video at that point, and I will start a new one to talk about how we're going to use numbers to associate with these units. Thank you.